The central limit theorem deals with something called a sampling distribution. So what we have here is a simulator that's going to allow us to play with different population distributions and see how a sampling distribution is created, as well as to see what it actually results in and what it means. So to start with, we're just going to go through this and see what exactly this is doing. So what we've got here is a population that is normally distributed, approximately. It is got a roughly bell-shaped curve to it. It is highest in the middle, symmetric, and decreasing to both sides. Now, if you look at the scale on the axes here, the x-axis, it goes from 0 up to 32. So all of our data values are going to be from 0 to 32. Now, what we're going to start with is from the population, we're going to draw a random sample of 5 data points. And for that random sample of 5 data points, we're going to calculate the mean. Well, we're not going to calculate it, the computer's going to do that. So what I'm going to do here in this second chart is I'm going to have it generate the sample, and we'll actually get to see it do that. I'll click the animated button and you'll see 5 random values drop down. And then underneath it down here is where you'll see the mean of that sample appear. So let's check it out. So it drops down 5 data values, and note that they are mostly kind of in that middle area, which follows with what we know about normal distributions. Within one standard deviation, you've got 68% of the data values, so there's like a 2/3 chance that when you pick a random value, it's going to be somewhere in there. Okay, so what we got is 5 values that were roughly in there, and the mean of them, if we want to actually count these out, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got the number 13 twice, the number 17, 19, and 21. And that has an average of 17. Okay, so we're in the center. Our mean actually landed kind of pretty much dead center of the distribution, which is, well, what you might expect. That's in a normal distribution, the mean is in the dead center. Now, that's not always going to happen. So what I'm going to do is I'm going to click this again. We're going to generate another sample of 5 data values. So again, we got data values in the center. This time we got one that's kind of like right at the edge of one standard deviation away. And then we got a couple that are a little bit further out. Now that can happen. I mean, it's not impossible. As we said, about 2/3 of the data is within one standard deviation, but there's still a third of it that is beyond that, to either the left or the right. So it's not, it might be a little on the unusual side, but it's not horrendously weird to have to have gotten a data value that's over here to the left a little bit. So what we've got now is a new sample with a new mean. And what we can see is that even though there's a little bit more kind of spread, a little bit more variation in our data values here, they're not all clumped in the middle like the last one. We've got some that stretch further out to each side. But the mean is still kind of towards the center. Now, it's not like the last one. It's not dead center. It's a little bit off to the left. But again, that's possible. I mean, it's not like you're going to get the same mean every single time. So let's try another one. So again, we're going to drop in 5 data values, and again, this time they're all kind of clumped towards the middle, and the mean is kind of towards the center as well. Let's do another. Okay, this time we got two data values that were kind of far out there to the left. We really didn't get any that were right in the middle, but we did get these, which are, you know, towards the right edge of that one standard deviation thing. But this middle of it is right here again. So even though we got a lot of variation, even we had that relatively uncommon result of a couple of data values way out here to the left, the mean is still in the middle because these data values over here are still in that kind of normal range of one standard deviation, and they are enough to balance out the fact that these ones are way off to the left. So once again, we see here, we got most of our data values, again, pretty tight in towards the middle, one a little bit far off to the left, and one kind of far out to the right. Again, not impossible, a little unusual, but the idea is that the two that are way out to either side kind of balance each other out in the middle, and we end up with a mean that is, once again, kind of right towards the center of the distribution. Now, the idea is if we continue to do this, if I continue to draw samples, and I do this over and over and over again, we're going to start to see the sample means stack up in here in a particular arrangement. So what I'm going to do is I'm going to have it do 5 samples at a time. So what we're going to see this time is we're not going to see all 5 data values drop down there. It's going to pick 5 data values, and then it's just going to calculate the mean and put the mean down here. And it's going to do that 5 times. Okay, so we got more means. Compared to what we had before, we've got a couple more over here, we've got a couple over here, but again, still kind of clumped towards the center. All right, well, let's try again. Another 5. Oh, look, again, still kind of clumped in towards the center like that. Nothing particularly recognizable yet, but we still got most of our sample means clumped right in the middle, with maybe a couple a little bit out to one side or the other. Same idea, we're getting a clump in the middle. In fact, that clump in the middle is getting higher and higher. We're getting more and more samples that had a mean right in the middle. And maybe we're picking up an occasional 1 or 2 towards the outer edge. And if I keep doing this, now, it's not that the bar shrunk. You'll notice over here the scale had to change to account for the fact that we now have 12 sample means here. So in stretching out to fit the 12, it kind of gave the appearance that some of the smaller bars shrunk. Now again, we're not seeing a whole lot of stuff going on here, but we're only up to 55 samples. Imagine I sit here and click the animated button 55 times. You know, that's what we're up to here. Well, let's keep going. I'm going to keep on clicking it a bunch of times, and it doesn't seem to have a tremendously recognizable form here, except if we keep going far enough, if I keep doing this, what you'll start to see is that it's going to start to get high in the middle while staying low on each end. Because, as we've been seeing, most of the time, the sample means are kind of towards where the population mean is. With occasionally you get a sample that has a particularly low or particularly high mean, but for the most part, they stay pretty close in here. And as we keep going and going and going, you're going to start to see a distribution that comes out looking actually kind of like a normal distribution. High in the middle, dropping low on both sides in a roughly symmetrical way. I mean, we're up to, if you're keeping an eye on the repetitions over here, we're up to 655 samples. And we are definitely getting something of a normal distribution here. It's not perfect yet, but aside from the middle here being a little bit off, it is pretty symmetric. And it's only going to shape up better and better and better as we go. Okay, well obviously this is getting a little ridiculous with clicking the 5 button a whole bunch of times. That's what the 10,000 is for. Instead of just doing 5 samples at a time, what if we do 10,000 and speed up this process? Ah, we see a much more drastic change, but we also see a more definable kind of normal shape there. In fact, let me click on this for a quick moment. Look at the shape of a continuous normal distribution. And look at how well the rectangles, of course they're not going to be perfect because it's a histogram, they're rectangles, everything's squared off, but they do certainly have that kind of normal shape going to them. So, I mean, it took us over 10,000 before we really got a solid view of that normal distribution there. But we did eventually get there. And that's kind of the idea of this, is that, you know, in real life, would we actually sit there and do a sample 11,000 times? No. But what it is telling us is that if 11,000 samples were done, most of the sample means should be in here. Occasionally you might get a sample mean that's a little bit further off to one side or the other, but for the most part your sample means should be pretty close to what the population mean is. I mean, the whole idea of the sample mean is to estimate the population mean, and sure enough, most of the time we're going to get a pretty decent estimate. Now, there are several things that can affect this. One of them is the sample size. We actually are using a very small sample size here. If we use a larger sample size, like 10, or better yet, something more like 25 or 50 or 100, we're going to see that it doesn't take nearly so many repetitions in order to see this shape come out. The shape will come out a lot faster. Another thing is that we're looking at a population that is also normally distributed. So perhaps it's not unusual that if the population is normally distributed, that we get a normal distribution among its sample means. Because, again, most of the data values are going to come from the middle. Occasionally we'll get one that's further out to the side, but usually it's only 1 or maybe 2 data values, or just a small number of them that are out here, and the larger number that are in the middle are enough to kind of outweigh that. Same thing if, to the other side. We might get a couple of data values out here, but usually the larger number of data values is in the middle, and is enough to outweigh it and keep the mean towards the middle. Now, if we change the distribution of the population, which we will do in a moment, we might see that it takes a little bit longer to conform to this, but eventually it's going to conform to it. So, let me clear these all off. Let's try a uniform distribution. A uniform distribution means that every data value has an equal chance of being selected. So instead of the ones in the middle being most often the thing, having the highest probability of being selected, everything has an equal chance, much like rolling a 6-sided die. Each number can come up with an equal probability. So what we're going to see here is we're going to see less clumping of the individual data values towards the middle, and we're going to see the data values in our sample much more spread out. So we're going to keep it with 5, a sample of 5 for the moment, so the animation is, manageable here. So let's see, 5 randomly selected data values. Okay, so because there's an equal probability, we can't really say, oh, we're more likely to get data values in the middle or towards one end or the other. As it so happens, we happen to get a bunch of low data values with one higher one, and that balances out somewhere around here. Okay, let's check a different sample. This sample is very different than the last one. This time we got several higher values, one in the middle and one very low data value, and this time the mean is off to the side over here. Another sample, again, seems to be more towards the left. This sample seems to be a little bit more balanced. These two data values are right towards the center, and then we've got three data values a little bit off towards the right, but fairly well balanced there. This one is much better balanced. We do have data values far to the left, but also kind of far to the right, and they balanced each other out and gave us a mean kind of towards the middle. Now again, we could sit here for a while doing individual samples, or we can do several at a time. Now, if we do 5 samples at a time, well, I mean, the sample means seem to be all kind of spread out a bit. Note, though, that you're not getting any sample means that are way out to the left like this, or way out to the right like that. Now, when you think about it, the only way to get a sample mean of, say, 1 or 2, that would mean that all of the data values, all 5 in our sample, would have to be this small. Because even one large data value would be enough to yank that mean over. As we saw in our first few samples that we did before, where we had 4 data values way over here at the left and 1 at the right, and it was enough to pull our sample mean over to the right a little ways. The only way we're going to get a sample mean of 1 or 2 is if all of the data values are very, very, very small, which is definitely possible, but given that they all have an equal probability of being selected, chances of getting all 5 of them in one tiny little spot like that are not very good. In fact, in the ones that we did look at the animations for, they were decently spread out. So the chances of getting them all clumped down at one end or at the other end are very, very low, and that's why we're not seeing any sample means out here. We are seeing some sample means that are a bit ways to the left or a bit of the ways to the right, but for the most part, they seem to still be, they have a wide grouping, but they are still grouped, kind of towards the center, which, again, is what a mean is supposed to be doing, measuring the center. So, again, we can sit here for a while adding on samples of, 5 samples at a time, but it's going to take a very long time to get where we need to go. So what I'm going to do is jump up and add 10,000 samples. And look at that. We're now at 10,130 samples, and look at the shape. It's definitely not perfect, but it definitely has that bell shape symmetry to it. Again, not perfect. Let's add another 10,000 in and see if it shapes up any. Oh, we see a little bit of a change, yes. A little bit of a change, a little bit of a change. Okay, well in this case we're up to 50,000 samples, so it's definitely taking a lot more than it did before. Before we see this emerge properly. So since it's taking so many, let me save some time, and instead of going 10,000 at a time, let's do 100,000. We're up to 250,000 samples right now, and at this point we've got a pretty good symmetric curve going. Again, not perfect, but pretty good. At this point, even adding a few 100,000 more, we're not going to see much variation. But we've already got the pretty symmetric normal shape going on there. Now, time to start paying attention to some of these things over here. these are some of the statistics about the population, and these are the statistics about the distribution of the sample means. The population has a mean of 16, which kind of makes sense. If the values go from 0 to 32 and they all have the same probability, the mean's going to be in the middle. The median is not of concern here, not to what we're doing. And then the standard deviation here is 9.52. So that's indicated by this red bar underneath. That the standard deviation, the value to go one standard deviation out to either side to encompass a certain percentage of the data set. And it's got to be pretty wide in this case because the distribution is uniform. So you have just as a high probability of selecting a single value that's high or low as you do right in the middle. So come down here and take a look at the mean, 15.99. That's virtually identical to the mean of 16 up here. That's interesting. Now we are going to notice a difference in the standard deviation because the normal shape of this means that we're low at the outsides and high in the middle. So remember, up here we had a wide standard deviation because there was just as large of a probability of selecting a data value from one side or the other as there is something in the middle. But here, the probability of getting a sample mean that's very low or very high, those probabilities are negligible. So we don't need as wide of a standard deviation to encompass the same percentage of our data here. And again, remember, the reason for this is it might be not unusual to select an individual data value that's 0 or 1 or 2, but to get a sample mean that's 0 or 1 or 2 means that all 5 values in our sample would have to be very, very low. And that is unusual to get all 5 of them very, very low. Or on the other end, to have a sample mean of 30 or 31 or 32 means that all 5 of our sample data values would have to be around 30, 31, 32. And while it's not unusual to have a single value from over here, getting all 5 at this end with none anywhere else is highly unusual. It's much more usual to have a decent spread of our sample data, and that ends up getting balanced out somewhere towards the middle. So even though we have a different distribution here, all it did was end up taking more repetitions to see the pattern emerge, but the pattern still did eventually emerge. A normally distributed distribution, not of the data. The data was a uniform distribution, but the sample means, the mean of each of our samples, 550,130 samples were drawn, and 550,130 means were calculated. And this is how they all laid out. Now, does it always have to take quite that many? No. Again, one of the factors is sample size. So let's try this again. Let me clear all this out. But this time let's up the sample size. We have several different sample sizes we can play with here. Let's go to the biggest, 25. Now this time, if I click animated, you're going to see 25 values drop. And again, you're going to see that they're pretty well all spread out. Some of the values get picked multiple times. Others only get picked once, but check that out. You do have some data values that are very, very high, but also some that are very, very low. But you got them also scattered out throughout, and look at where the mean landed. The mean is pretty much dead center. Well, again, I mean, now that we're looking at a sample of 25, imagine if we said before getting 5 data values that were all 0, 1, and 2, if that was unusual, imagine getting 25 data values that are all that low. In a sample of 25, you're much, much more likely to get a balance. Yes, you're likely to get a very high or a very low 1 or 2 or 3, but you're much more likely to get 10 or 15 or 20 that are more towards the middle. Let's check it again. Well, yes, we are getting a couple of data values really high, some that are really low, but they're pretty well scattered about throughout, and look where the mean drops. Right next to the other one. I mean, they're again, it's pretty much dead center. All right, let's speed this up a bit. 5 samples, all 5 of them, and along with the original 2, are clustered right around the middle. 5 more, still clustered towards the middle. We did pick one up that's a little bit further to the right, but we've got, what, 5 sample means all right in the center? Once again, what we're seeing is they're all kind of clumped towards the middle. Notice that we don't have any way out to the sides, of course, but we don't even have any that are over here. The reason is, again, that now we're doing 25. It's going to be harder to get that variation where we have a sample mean, even that's not all the way over at the left, but just a little bit to the left, because in 25 data values, we're likely to get a pretty good distribution of the data here. Let's jump up 10,000. Look at that. We are already seeing that normal shape. Again, not perfect, but pretty darn close. And it only took us 10,000 this time, as opposed to 500,000 last time. We can add another 10,000, another 10,000, but we're not going to see very much difference. Now, check out the sample means. Again, the mean and standard deviation up here are the same as they were in the previous set because it's the same distribution of the population. But what we see now down here is, again, the mean and standard deviation. The mean here is the same as the mean of the population. The standard deviation is even smaller than it was before. Prior, it was about 4.7 or so. Now it's down to 1.9. It's a tighter distribution. And the reason for that is that it's much, much harder to get data sets, samples, whose means are to the left or right. I mean, it's virtually impossible now, because if it was, again, if getting 5 values all clumped down here was very difficult, getting 25 clumped down here is going to be virtually impossible. 25 selections, and all of them end up down here, and none of them come from anywhere else. That's incredibly unlikely. Even to have a mean that's over here means we'd still have to have the vast majority of our data values coming from just one side of the data set and none from the other. Even that's incredibly unlikely at this point. So what we see is that the sample means are even tighter in than before. It's even harder to get variation over here. And that causes this to fit into the normal distribution much more quickly. Now, we can play with this in all different kinds of ways. A custom distribution. One where I can draw any kind of distribution that I want here, including something completely bizarre and random like this. But if we do it with a large enough sample size, and we do it enough times, we're still going to see it come out with a normal distribution. And not only that, look at the means. the mean of the distribution of sample means is the same as the mean of the population. The standard deviation is different, but actually, if you take a good look at that, the standard deviation of the sample means is 5 times smaller than the standard deviation of the population. 5, which corresponds to the square root of our sample size. So in the other video, we're going to see the formulas for these, but the basic idea of this is that regardless of the population and how the population is distributed, if we do enough samples, we will eventually see the distribution of sample means approaching something that is approximately normal. It may not be perfect, and certainly the wackier this population distribution is, the less exact the sampling distribution will fit to a normal, but it does eventually get there. Things that help is, the more normal the population is, the faster you'll see this pattern emerge, and the larger the sample size, the faster you'll see this pattern emerge. Now, all of that being said, the idea isn't that we would actually sit there ever and do 400,000 samples. That's unrealistic to do in real life. However, it does give us kind of a foundation for saying how reasonable is the one sample that we actually do if we do pull a single sample. How reasonable is it that the sample mean we calculate is actually a decent estimate of the population mean? And the idea is that, well, if our sample size is big enough, and if the population is roughly normally distributed, we've got a pretty good chance of getting a good sample mean that estimates the population mean. The further off this is, or the smaller the sample is, the less likely it is that we're going to get a good estimate, but we probably still are going to get a decent one. It's just not quite as strong of a possibility. So as I said, the other video for this lesson is going to explore the formulas and the workings of this, as well as actually, making a comparison between a population and the population of sample means. But this tool here is a good one to just kind of play with this. As you can see up here, the URL, if you want to play with it on your own, is up there, and you can try it out. It's kind of interesting to play with a little bit. Now, there are other things in here that we did not talk about, such as, for example, we did a sampling distribution of the mean. You can do sampling distribution for a number of other measurements as well. That is beyond the scope of this course. There's other things here, like it mentions skew and kurtosis. Don't worry about those. Those are, again, far beyond the nature of this course. Not things you need to worry about. We didn't even use the median. All we really paid attention to here was the mean and standard deviation of the population itself, and the mean and standard deviation of the sample means, just to see how well they line up against each other. So check out the other video to see some examples of actually how we would apply this to some problems, and the formulas that are going to go into the relationship between the means and standard deviations of these two distributions.